This example automates the 12 different fault types with a strong grid in PSCAD. So some changes. The file name is Solar4. That's a base file name. I chose the average model just so I can run with a longer time step in the interest of time. And remember, at least from the standpoint of harmonics, the average model is pretty close to the detailed model anyway. Chose a longer time step, 100 microseconds, and a shorter time, just because that's all I really need to see in the plots. The grid impedance there has to be the strong source 10 ohms, and then on the ComTrade recorder, there's a file name that is going to be changed automatically from a Python script, and then my recording time step is 100 microseconds. So those you won't have to do it in this example, but in setting up this case to run, those are some of the things you have to set up for the base condition. But the system load flow didn't change at all. So what the bulk of this example is going to be about is the Python script that automates that fault simulation. So it is in your PSCAD directory. The name of the file is faultscript.py. Here are the preconditions. PSCAD has been launched. You have the Solar4 project, so it's going to find it by name. You set up your time step and your simulation time, and then the components to be modeled have been assigned unique names. So this is important. I should show that. So the recorder, notice I gave it a name, this name for identification. Sometimes these are left blank, but we don't want that because the Python script is going to need to find it by name. The other thing is, in this case, the timed fault logic, probably not, but that fault inductance, that's going to be fault L, if you can read that. And then the fault type, that's just fault. Okay. So whenever we have to change something by name, identified in the script, we want to give it a name, a unique name. It's going to make our life a lot easier. So this, we're going to import the mhi.pscad package to automate PSCAD. I set up a table to kind of govern the execution of each case. So I have a mnemonic for the file name, ABCG80. So this is the three-phase to ground fault with 80% retained voltage, and this is the inductance that's going to achieve that. The running of the application, so this is kind of short. Verify the preconditions, so it's going to look for PSCAD running. That first line of code there will launch PSCAD, but then you can't really predict whether your project is loaded in the workspace. So I would ask you to open it and make sure that Solar4 is there. This line is going to figure out, find it by name. And then this next few lines of code here, I'm looking for those three objects I just showed you by name. I want to know the fault inductance, the fault switching configuration, and then the ComTrade recorder, because I need to change the file name, so I write each fault case to a unique file. Let's do this. Well, I won't do this, but you can change this to true. If you don't know the parameter names for the fault, then you can do this. We'll just do that. All right. The only time we'll have to show it. So you do this when you're developing a script the first time to know what parameters to change and what names to use. We're going to time how long it takes to run these. And then for each row in that table, I had the table of 12 cases up above. We're going to pick out the tag, the ABCG80, for example. And we're going to set like the fault inductance. I'm going to look up on the table whatever that L value was. So it's going to look up here, 0.1057 is going to be the first value. The first value of the tag is going to be ABCG80, and so I'm going to change the recorder, its F name, to that ABCG80 for the first case. So that's the syntax of how to modify PSCAD objects from a Python script. And you will see those changes appear on the schematic if you were to watch. And the other more complicated aspect of this is to change the actual fault type. So I'm just looking at the name. If I see the lowercase a in that tag, ABCG80, then I know phase A is involved. Likewise for phase B, C, and ground. And then I set the fault parameters, the switching configurations, based on those 4 flags, A, B, C, or G. All right, at this point, I am going to be ready to run. So let's see. The way to run this is Python fault script. You don't have to be case sensitive, but I'm going to mark that for you so you can see it, what I typed in there. You may have other ways to launch a Python script, but I like the command line. So actually, you only have to type this, Python fault script up, py, and with any luck, it'll go. All right, so this first part is finding all the projects that are in the workspace. The FaultAutomation project had found that, and now it's simulating 1 to 12 cases. This takes a while, but if I can switch over to PSCAD, notice that the progress update was being updated there at this bottom status bar, and now it's going to, it's writing ComTrade files, and it's going to start another case in a little bit here. And there you see the next one starting. So we're going to stop here. We're not going to wait for them all to finish on the video. When I just ran that, it did not show the parameters for the components I'm interested in, so I do want to show that. That's this block right here. I'm not going to rerun the cases, so I'm going to quit when that's done. The reason it didn't display the first time is I was running a different copy of the Python script, so when I made the change, it did not actually execute that changed file. But anyway, we're going to run that case again. And so the inductor parameters, let's see, I'll change the color. The inductor parameters, you can see that the name for fault L is fault L, and the value is 0.0264. So that was the last value it was left at. And then we have the parameter of the recorder, so we know F name is there. ABCG50 was the last one it was left at, and then there's all these other parameters that we don't have to set in this case. But it is interesting to see what parameters are available to set for new components that we haven't worked with before. Now the simulation is complete. I've opened the Jupyter Notebook cplot4 in the browser. I'm going to load the support functions for ComTrade, for Matplotlib. No, this doesn't change. Some of the plot formatting changes a little bit. I'm going to configure for PSCAD results import, so I didn't have to change any of those paths. And this one is going to import the case data. So in this case, before I think I've only imported 1 or 2 files at a time, but this again is table driven, so I'm going to import all 12 cases at once, by file name. And this doesn't take all that long. They're all done. So I imported 10 channels from each of the cases. And I'm going to plot them all on top of each other so you can see some cases the inverter doesn't ride through, so the power doesn't actually recover to 1, but it's allowed to not ride through some of those faults because they last for 0.3 seconds. So that was the systematic fault automation example with the strong grid. Some of these model responses may not be what you expect, and so you would want to dig into details of the model. So for example, this frequency, why does it go down to 20 hertz or even down to 10 hertz? Could be a feature or an aspect of the frequency meter, or it could be something with the IVR model, but that isn't our focus here today.